day and welcome once again to our class. In today's class, we'll be looking at the application of the monotone convergence theorem. Meaning that what? We'll be using the monotone convergence theorem to solve questions. The first question I'll be looking at, it says, using MCT, that's using the monotone convergence theorem, prove that 5 raised to power n over n factorial is either convergent or divergent. The first thing we need to do is to recall MCT. It says that a monotone sequence is convergent if and only if it is bounded. So to solve questions like this, the first thing we need to prove that it is monotonic, that the sequence is monotonic. Then we prove that it is bounded. We can then conclude by MCT that it is convergent. I want to show that it is monotonic. It is monotonic means that what? It is either increasing or increasing. Now let a sub n equals to 5 raised to power n over n factorial. A sub n plus 1 will be what? 5 raised to power n sub 1 over n plus 1 factorial. And that is what? 5 raised to power n times 5 over n plus 1 into n factorial. And that still gives us what? 5 raised to power n over n factorial times 5 over n plus 1. Now, for a sub n to be increasing, by definition of monotone increasing sequence, it implies that a sub n is less than or equal to a sub n plus 1. And that implies that a sub n plus 1 is greater than or equal to a sub n. Divide both sides by a sub n. Therefore, a sub n plus 1 over a sub n will be greater than or equals to 1. Now, if we divide these two, a sub n plus 1 over a sub n will be 5 to power n over n factorial into 5 over n plus 1 over 5 to power n over n factorial. This removes this. Therefore, a sub n plus 1 over a sub n is equal to 5 over n plus 1. Is equal to 5 over n plus 1. We want to show that 5 over n plus 1 is greater than or equal to 1. If n is equal to 1, 5 over n plus 1 is equal to 5 over 2. and that's 2.5 greater than or equal to 1. If n is equal to 2, this gives us 5/3, which is also greater than or equal to 1. It is greater than 1. If n is equal to 3, this is 5/4, and that is 1.25. It is greater than 1. If n is equal to 4, this is 5/5, which is greater than or equal to 1. But if n is equal to 9, then this gives us what? 5/10, and this is 0.5, which is not greater than 1. So what can we say about this sequence? It shows that this sequence is an eventually decreasing sequence. However, sequence 5 to the power n over n factorial is an ultimately decreasing sequence, and so it is monotonic. We have been able to show that is monotonic. The next thing is to show that it is bounded. By definition of bounded sequence, a sequence is bounded if it has both a lower bound and an upper bound. But since this is a decreasing sequence, it means that the first term of the sequence is an upper bound. Does the sequence have a lower bound? Let's find the limits as n approaches infinity. Limit as n approaches infinity of a sub n plus, that is limit as n tends to infinity of 5 raised to power n over n factorial into 5/n plus 1. That is what? The limit as n tends to infinity of 5 raised to power n over n factorial into the limit as n tends to infinity of 5/n plus 1. And so, by the time we take the limits, that's 0 into 0. Therefore, the limit as n tends to infinity is equal to 0. Therefore, it has a lower bound. Therefore, it has a lower bound, and as such, a sub n is bounded. Therefore, since a sub n is monotone and bounded by monotone convergence theorem, a sub n is convergent, and it converges to where? Converges to 0. Look at another example. Example 2, prove that the sequence defined by S1 is equal to 1 and Sn plus 1 is equal to square root of 1 plus Sn is convergent. Using the monotone convergence theorem, the monotone convergence theorem says a monotone sequence is convergent if and only if it is bounded. And that implies that what? A monotone sequence is bounded. If a monotone sequence is bounded, then it is convergent. Therefore, as I said earlier on, it will show that it is monotone. That is, it is either increasing or decreasing. It will show that it is bounded. That it has an upper bound and a lower bound. And then we can conclude that it is convergent or it is divergent, as the case may be. So let's go ahead to show that this sequence is monotone. Let's consider the terms of the sequence. S1 consider the terms of the sequence. S1 is 1. S2 will be the square root of 2, and that is 1.414. S3 will be the square root of 1 plus root 2, and that is 1.554. This seems like an increasing sequence, but we need to be sure that it is increasing. Since S1 is less than S2 and S2 is less than S3, this seems like an increasing sequence. For it to be increasing, then it implies that what? Sn plus 1 will be greater than Sn. When n is equal to 1, S2 is greater than S1. Sn plus 2 will be greater than Sn plus 1. But Sn plus 2 is equal to what? The square root of 1 plus the square root of Sn plus 1. And Sn plus 1 is greater than Sn. Therefore, Sn plus 2 will be greater than the square root of 1 plus the square root of Sn. And so Sn plus 2 is truly greater than Sn plus 1. Therefore, Sn is increasing, and so Sn is monotonic. The next question is Sn bounded? Because they have been able to show that it is monotone. Is Sn bounded? Again, we need to recall the definition for bounded sequence. By definition of bounded sequence, A sequence is bounded if it has a lower bound and an upper bound. A sequence is bounded if it has a lower bound and an upper bound. Assume Sn has an upper bound 2 for all n belonging to natural number. This implies that the absolute value of Sn is less than or equal to 2. By induction, if n is equal to 1, our S1 is that, and that is less than or equal to 2. Therefore, Sn is less than or equal to 2. Is this true? We want to show that Sn plus 1 will also be less than or equal to 2. What is our Sn plus 1? Sn plus 1 is equal to the square root of 1 plus Sn. But Sn is less than 2, as we have assumed 2 to be the upper bound. It means that what? Sn plus 1 will be less than or equal to the square root of 1 plus 2, which is less than or equal to the square root of 3, and that is less than 2. Therefore, we can conclude that the sequence is bounded. And if the sequence is both monotone and bounded, therefore, by MCT, the sequence is convergent. Since Sn is both monotone and bounded, therefore, by MCT, Sn is convergent. And if Sn is convergent, that means the limit exists. So what is the limit? Let L equals to the limit as n tends to infinity of Sn. But Sn plus 1 is equal to the square root of 1 plus Sn. Sn plus 1 is equal to the square root of 1 plus Sn. Therefore, the limit as n tends to infinity of Sn plus 1 is equal to the limit as n tends to infinity of square root of 1 plus Sn. Therefore, limit as n tends to infinity of Sn plus 1 is equal to the square root of 1 plus L. Since Sn plus 1 and Sn will have the same limit, it means that what? Since Sn and Sn plus 1 will have the same limit, it means that limit as n tends to infinity of Sn plus 1 is equal to limit as n tends to infinity of Sn, and that is L. Therefore, L is equal equal to the square root of 1 plus L. That implies that L squared is equal to the square root of 1 plus L. So L squared minus L minus 1 is equal to 0. We have L to be equal to 1 plus square root 5, 1 plus or minus square root 5 over 2. That implies that our L is equal to 1 plus root 5 over 2, or L is equal to 1 minus root 5 over 2. That implies that L is 1.618. Therefore, the sequence S1 equals 1 and Sn plus 1 equals square root of 1 plus Sn is convergent, and it converges to 1.618. Consider the sequence A1 is equal to 1 and An plus 1 equals the square root of An plus 2. Show that the sequence is convergent. The monotone convergence theorem. A monotone sequence is convergent if and only if it is bounded. That implies that if a monotone sequence is bounded, then it is convergent. So we'll go ahead to show that that sequence is monotone. We'll go ahead to show that the sequence is bounded, and then we can conclude that it is convergent. To show that it is monotone, let us consider the terms of the sequence. A1 is 1. A2 will be equal to what? The square root of A1 plus 2, and that is square root of 1 plus 2. That is square root of 3. A3 will be the square root of A2 plus 2, and that is what? The square root of 3 plus 2. This shows A4 will be the square root of A3 plus 2, and I'm sure we can get what that is. Therefore, we can see that the terms of the sequence is between 0 and 2. That is 0 less than or equal to a sub n less than or equal to 2. This implies that 0 is less than or equal to a sub n plus 1, which is less than or equal to what? Since a sub n is less than or equal to 2, that is square root of 2 plus 2, and that is, therefore, 0 is less than or equal to a sub n plus 1, which is also less than or equal to 2. And that implies that since the terms of the sequence a sub n is between 0 and 2, our a sub n plus 1 also is between 0 and 2. 0 is less than or equal to a sub 1 less than or equal to 2. 0 less than or equal to a sub 2 less than or equal to 2. 0 less than or equal to a sub 3 less than or equal to 2. Therefore, the sequence has a lower bound 0 and an upper bound. This is for all n, and an upper bound 2. Therefore, the sequence is bounded. We have established that it is bounded. Is it increasing or is it decreasing? Is it monotone? For the sequence to be increasing, a sub n will be less than or equal to a sub n plus 1. That means a sub n will be less than or equal to what? The square root of a sub n plus 2. That implies that the square of a sub n is less than a sub n plus 2. That means that 0 is less than or equal to minus a sub n all square plus a sub n plus 2. And by the time we factorize this, our 0 will be less than what? 2 minus a sub n into 1 plus a sub n. And that implies that what? 0 is less than or equal to 2 minus a sub n, or 0 is less than or equal to 1 plus a sub n. This implies that a sub n is less than or equal to 2, or minus 1 is less than or equal to a sub n. And so this implies minus 1 less than or equal to a sub n less than or equal to 2. Therefore, a sub n is increasing. And since a sub n is increasing, therefore, a sub n is monotone. Therefore, a sub n is monotone and bounded, as we have initially shown before. Therefore, by MCT, since it is monotone and bounded, it means that what? A sub n is, it means that a sub n is converging. You can try your hands on the following. See if you are able to show that it is convergent. You can try your hands on the following. Show that it is convergence. So that it is convergent, and also find the limit. If you have gained anything from this video, give it a thumbs up, share with your colleagues and friends. Thank you. God bless you. I see you in the next video.